Okay, thanks for that. Thanks very much for the opportunity to speak with you this afternoon. I'd like to acknowledge my contributors here, Elena Kondrolova from Slovakia and Georgia Kuba, who's a technical researcher with me. And our study site is up here in Kalpam Station, just north of Renmark, in the Mallee area on the north side of the river. So this is part of the TERN, Terrestrial Ecosystem Research Network, and it's the component called OzFlux, and it's about measuring the carbon dioxide, water vapour and energy exchanges across major ecosystems of Australia, and that links into a world network of measurement and modelling, looking at the responses to various interventions associated with obviously on-ground interventions and climate variability and so on. And that links then into a system that's looking at the connection between the terrestrial system and the atmosphere with respect to the global circulation models. Since January of this year, when our data has become available to the world scene, we've had 102 downloads from all over the world that are about to look at and use our data. So this talks really about one component, talking about the water use over the Mallee and the measurement that we've made there, to look at how we might validate our estimation methods of evapotranspiration or evaporation, and then to assess the sensitivity of different methods of getting hold of leaf area index, which, as you'll see, is a very important part of describing how the exchange goes on between these systems. The map in the top left here has got the sites associated, the 25 sites that are currently associated with the OzFlux network, and you can see that they cover a very large number of the vegetation, major vegetation types in Australia. Here's our site here in the Mallee, which is representative of this Mallee eucalypt woodlands across southern Australia, right across into Western Australia. We're the only OzFlux site in South Australia, been running since August of 2010. The site is effectively, the main feature of it is a 20 metre high tower, which is instrumented. The critical bits of instrumentation are these two, so a sonic 3D anemometer here, and associated with it a open path infrared gas analyser. So what this is measuring is the concentration of CO2 and water vapour, and we're interested in the vertical exchange of those two gases up from the terrestrial surface up into the atmosphere. Here's the data is collected at 10 times a second and then aggregated up to 30-minute totals, and then downloaded every 6 hours to a website. There's the site address there, and you can see we've got temperature, wind run and velocity. Here's the absolute CO2 concentration, temperatures, rainfall and the energy that's coming into and out of the system. So let's just focus on the water part of it. The annual rainfall and evaporation total since August of 2010 up to June of 2015. And you can see in the latter half of 2010 that we had more rainfall and evaporation, so this was really the end of the millennium drought. 2011 was also a wetter year when rainfall exceeded evaporation. But then you can see in 2012, evaporation exceeded rainfall, and at that time, obviously, the vegetation is dependent on the rainfall which was stored from that wetter period. And you can see that it's very close. The median rainfall up in this side is about 250 millimetres a year. But you can see large variation from year to year. And when we have a look at the totals here, across this 5-year period, there's a 12% difference between the rainfall and evapotranspiration. That is, we've got 12% of the rainfall which has come into the system, has not been evaporated and is entering the groundwater system, entering the soil water storage in the groundwater system. And of course that's really fundamentally important to the survival of the species, to the vegetation in this kind of system. The estimates that we make from the measurements, the atmospheric measurements from the flux tower, are then calculated via a method called eddy covariance to come up with our estimate of evaporation. And we use that estimate together with the rainfall data to come up with a water balance. And here this is a water balance which is constructed for the top 2.5 metres of the soil profile. And we're checking that against, so that's our estimate, and we're checking that against neutron probe soil water measurements, again to that depth over time. And you can see very nicely that we're doing pretty well during this monotonic drying period. The change that we're measuring the soil water from the physical measurements of soil water are very close to our estimates here. Not so good down here, so our check with respect to our estimates relative to the direct measurements of change in soil water, not perfect, but we're pretty confident that we're getting pretty close to having a very good measure of the evapotranspiration. One thing that we can do is have a look when you get free water in the system, that is when immediately after rainfall and you've got water that's been intercepted by the vegetation and on the soil surface. That is immediately available for evaporation once it stops raining. And in summertime it only takes a day, just over a day. If we had clear days it'd probably take less than a day for that evaporation, that water to be completely evaporated out of the system, and now you're back into control of water loss both from the vegetation and from the soil surface. When you've got lower evaporation conditions during the other seasons and when you have likely more cloud cover immediately after rainfall, then it takes a bit longer to evaporate. Now there are various ways in which we can estimate evaporation. So we've talked about this eddy covariance method here. So that's from our measures from the flux tower. The most commonly used method to estimate evapotranspiration from our weather data, from the climate data, is the Penman-Monteith equation. So it's got energy terms in it, it's got the water vapour terms in here, how dry the air is, some temperature terms, and then it's related to the vegetation through these two resistance terms. In this one, it's the LAI, the leaf area index, which affects that resistance, and down here it's the height of the vegetation which influences this resistance term. Now that Penman-Monteith equation, commonly used, came from an original equation, the Penman equation, and this has got the same, you can see the same similar kind of terms in here, but it's got this wind function term in here. I calibrated that wind function term for southern Australia quite a few years ago, and we call that the Penman-Meyer equation because it's got that wind function term in there. But it assumes a vegetation with a leaf area index of 3, or greater than 3. In other words, we've got a closed canopy. We've got 3 square metres of green leaf area per square metre of soil or ground surface area. So it's a closed canopy and of course it can evaporate quite readily. So but we're interested in trying to get an estimate of the actual evaporation that we can check against our measured values, our estimated values from the flux tower. So there's an empirical equation that Joe Ritchie developed back in 1972, and of course if you know what this value is from our daily met data, and we can get a value from the flux tower at the time when we've got free water evaporation, we can back calculate and figure out what the effective leaf area is, which is what we do. So when evaporation from the soil plant system is not water limited, which is not very often in this kind of system because most of the time it is water limited, immediately after rainfall not water limited, then we can back calculate it and find out what that LAI is. So here's some outputs from that kind of calculation. So this is in June of 2013. The blue bars are the rainfall during June. Here we've got the up and down of the daily evaporation, which comes from measurements of the daily weather data and putting it through the Penman-Meyer equation. So that's what it comes up to. You know, you've got 3 millimetres or more on some days. Then you've got down here, the black line is the value of evaporation which comes from the flux data. So it's the latent energy term of that flux from the tower. So the estimate using eddy covariance. And you can see that's at a much lower value, less than 1, less than about 0.5 of a millimetre per day. And here, if we then use some matching points after rainfall and figure out what that effective LAI is and apply it, use our estimated daily potential evaporation term and correct it for the actual leaf area index, which is what this light green line shows, then you can see we end up with a very similar value estimate of the evapotranspiration. Here's what it looks like now. We've done to do another independent check. Here's the data from the 2010 right through to 2015. And again, the blue bars are the rainfall values. And you can see the dark red line here, the ups and downs, is the leaf area index, the inferred leaf area index from our back calculation from the daily weather data and getting back to an inferred leaf area index to match what we observed from the flux tower. And you can see the ups and downs, and you'll notice that the ups and downs are primarily associated with rainfall. So after rainfall we start to see the vegetation recover and put on a bit more leaf area. During dry periods, of course, it starts to shed a bit of leaf area. And now we've got this dark green line here, which is an independent estimate of green cover from the satellite data, the NDVI, the Normalised Difference Vegetation Index, from satellite data at 250 metre resolution. And you can see it matches very nicely. So, a little summary about evaporation of the mallee. The eddy covariance can track evaporation. It's not perfect, but it's certainly better than other methods. It gives you spatial sampling. Free water evaporates very rapidly in the summer. Evaporation can be calculated from weather data, so long as you've got a very good estimate of what your leaf area index. So it's really fundamental to get that value, both for the carbon, the amount of carbon that's going to be taken up, and the amount of water that's going to be evaporated. This system is mostly water limited. Tree water use is very conservative. If you see a water use of about 2 millimetres a day, that's a very high water use. Unlike agricultural crops, where you might see it up to 10 or 12 millimetres a day. Tree crop growth as available water is also conservative. It doesn't respond very rapidly after rainfall, and once you've got stored water, it's quite slow, so it's very conservative in that respect. We can calculate how much water is in this that the mallie's got available to it. We don't see roots. We won't see roots below about 10 metres because we get into the Blanchetown clay. So we can calculate that. And the NDVI, the satellite-derived data at 250 metres resolution, actually correlates very well with leaf area index and will give us an independent measure of that important parameter. So there we go, evaporation from mallee. Thank you.